Hi and welcome to a cloudy summer day here in Stockholm. I have a bit of context to give to this video. So every Wednesday we have a meeting in our group here. So this is Marcus Kowalewski's group at the Chemical Physics Department, where we can discuss basically anything and everything. So maybe somebody's read a new interesting paper, or there are some new results in the group that we can present and discuss. And also we have a recurring series on methods that are used for quantum dynamics and the kind of work that we are doing here. So in this video, I want to tell you about the method called multi-configurational time-dependent Hartree. So as a quick disclaimer, I should say that I haven't actually used this method. So I also encourage you to look at other sources and see what other people have to say about this method. But anyway, this is going to be then like a quick introduction to the method, and I really hope you find it useful. And with that, let's go. Right, so welcome to a presentation about multi-configurational time-dependent Hartree methods that I've been looking into lately. My source for this is this paper. So it's a good source actually. It's a bit longer, it's not just a paper, it's more of a teaching resource or something like that. I'm not exactly sure where it's from. So that means that it has a bit more of the details about what's going on rather than trying to read papers about this method. This was a useful source. So if you want to know more, I can recommend this. But there are a lot of pages, so I read the beginning chapters that sort of introduces the method and explains some of the derivations that underlies it. So basically, when we're working with quantum systems in numerical simulations, there are two approaches or two categories of methods. First one is to work with the Schrödinger equation using time-independent methods, in which case the objective is to diagonalize the Hamiltonian to find eigenstates, so like some set phi k there, and corresponding energy is Ek, and you can then express your state as a time evolution in terms of these states. Right. This is then an eigenvalue problem, formally, and the problem with this method might be that eigenstates can be difficult to find, though. Like, this is applicable in some situations, typically in situations where states are bound, because if your system also contains free states, then you're in the continuum, and eigenstates are very difficult to describe. They're uncountably infinite number of them. So in numerical situations, that's difficult. Sorry, it's double skips here sometimes. Second, the third point is that this might not be so suitable for time-dependent Hamiltonians, right? Because eigenvalues and eigenenergies would change then. So you calculated them once, but that's only valid for one moment in time. The second approach is to do use time-dependent methods. Here we use the Hamiltonian for the system to do time evolution from an initial condition of initial state of the system. So the working equation is shown here. You have psi of t equals some time evolution, e to the basically the Hamiltonian, acting on some initial state. So instead of eigenvalue problem, we have an initial value problem, formally speaking. Though this can seem very sort of deceptively simple, this equation, you have an initial state and you time evolve it. But the problem is that the Hilbert space for this state, psi, can often be enormous. So to just describe the state somehow is difficult. But when we're talking about numerical methods, because there are many situations in which analytical methods are not available for other reasons. Right, so next thing, I think I thought I always like to ground things that we're talking about, so I'm going to go back a little bit and make a review about things that most of you already know about, but just like to see where we're coming from, and then approach MCTDH as a solution to the problem description. So what is the problem description? We're working with quantum mechanics. The simplest system that you can consider is a single particle in one dimension. And then in the position basis, we can express the state psi as a complex wave function. So this is shown here with a plot then. We are just considering 1 degree of freedom or one dimension, so we can actually plot the full wave function. And then what happens when you consider 2 particles in one dimension, which is like where we want to go, like we want to add more particles to our systems. So the next simplest example is just 2 particles, both in one dimension. And for a long time, my mental picture was something like this. Before I had actually studied these systems, just taking the introductory quantum mechanics courses, like, well, you have 2 wave functions, I suppose, for 2 particles. You have 1 wave function for a single particle. But this is not the correct description, as you all know. That what you should do instead is that you take the coordinate axes of for both of your degrees of freedom, x1, x2, and you form a plane, so they multiply rather than add. And now I'm running out of axes to describe the wave function on, because I want to have there is the real and the imaginary component. So instead I'm using the third axis to show the absolute value of the wave function. Then I can use some colors to show a phase. So this is just like an arbitrary function that I plotted to illustrate that there is some function on this space. And this function is describing the state of 2 particles, both living in one dimension. So, basic stuff. What happens if you have one of those particles have spin half? Because in a lot of the things we are doing, we're dealing with fermions. And this is basically what happens. So, or at least one way to illustrate it. I mean, there are many ways to try and plot these things, but it's getting increasingly difficult anyway. The point here is that we now have sort of double the amount of information, because we need to describe it we choose some arbitrary direction of spin, and then we have a wave function for spin up and a wave function for spin down. And it kind of looks in this picture like we have 2 functions. Now, that's not the proper way to think about it. This is a limitation of the plotting. This is in fact a single function. Then if both particles have spin, then again we multiply the number of spin configurations. We have up, 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 down, down, up, and down, down, and the wave functions, the amount of data that we need to describe the system is multiplied from the previous. And then what about the situation that we're actually interested in? Well, n particles in 3 dimensions, and then m of those have spin half. This is some arbitrary atom or molecule or something like that. This is impossible to draw, because we're supposed to have each 3 dimensions contributes with 3 axes, and then for each particle you multiply with 3 additional axes. They're all orthogonal to all the rest, and then we need to multiply those for each time we have spin half. So it's impossible to draw a function on this, impossible to show it. We don't have enough spatial dimensions in the world in this world to sort of give good representation, but this is my best effort, like it's just a bunch of dimensions. And on top of this, we should describe a wave function. So then this kind of underlies why these problems are hard to deal with, why the state description psi is something difficult. So there is also some more details to point out, that the fermionic degrees of freedoms are antisymmetric under permutation of space and spin. On this space, we want to find like eigenfunctions if we're doing the time independent approach, or do time evolution if we do the time dependent approach under a nonlinear Hamiltonian that looks like this, or at least this is this Hamiltonian does not include spin interactions, for instance, magnetic interactions. So this is a bit simplified already, but still very complicated, especially since it's non-linear in nature. So this is hard, right? This is basically the conclusion. And this is why we need to have numerical methods such as the one that we're going to talk about today, that includes simplifications. So what kind of strategies do we have to deal with this difficult problem? Basically there are two attacks. Strategy one is to simplify the Hamiltonian, and the Born-Oppenheimer approximation is a strategy to do that, which neglects the coupling between nuclear and electronic degrees of freedom. The next strategy is to simplify the state, the Born-Oppenheimer approximation again allows this, because when we have removed this coupling between nuclear and electronic degrees of freedom, we can treat electrons and nuclei separately. First one, the electrons, and then the nuclei. And another strategy to simplify psi is to restrict the functions on this enormous space to some family of functions. So instead of allowing for any arbitrary function on this space, we're like limiting the number of the types of functions that we can describe. So what is the procedure? Well, you know this. We calculate energies for position eigenstates of the nuclei in a quantum chemistry calculation. This hides the non-linearity of the interaction between electronic degrees of freedom in this potential. We calculate. This also hides this explicit state of the electronic degrees of freedom, so we don't need to deal with that after this calculation. And then we can do time evolution of nuclear degrees of freedom on a potential. It's obviously not the only procedure, but this is the kind of procedure that I'm working with, and it's quite common. And then, as I said before, we can also restrict the nuclear wave function to some family of functions. Even though we have followed this procedure where we simplify the problem in several steps, we still have enough nuclear degrees of freedom left that it's difficult to model. Then again, we do restriction of the nuclear wave function. So this is then the final point here, number 4, that actually it's number 5. I have 4 twice. Okay, point number 5, that we're going to restrict the nuclear wave function so that it's easier to deal with. So the basic strategy for this is to use a Hartree product. So what we actually want to model is the left-hand side here, which is psi, some arbitrary functions of some arbitrary number of dimensions depending on the problem, x1 to xn, and also in this case then, if we're talking about the nuclear wave function, we probably don't need to deal with any spins or anything like that. So it's just the spatial dimensions. So then one way to do this is to say, well, let's take n functions of 1 dimension or 3 dimensions, so depending on, x here is written as vectors, but this, depending on the problem, it's either 1 or 3 dimensions, so I guess it can be 2 dimensions too. But typically it could be 1 dimension. But anyway, instead of expressing psi as a general function of these n coordinates, we choose n functions of 1 coordinate and just multiply them together. And that gives obviously a function of n dimensions on this space. Let's see, right, and the corresponding procedure, which you all know, for doing quantum chemistry, is the Slater determinant. So this is the same for all intents and purposes. It's also a Hartree product. It's just that we take the same Hartree product and add it together with itself, permuting and swapping the signs, so that what we end up with after the Slater determinant is sort of carried out is an anti-symmetric version of the Hartree product. Because we know that the fermionic wave function should be antisymmetric, we make sure that the function is antisymmetric to begin with. But it's basically the same limitation, the Hartree product and the Slater determinant. Right, let's see. So the important part here is to see that this function, this Hartree product, is not able to describe any imaginable function, but instead is limited to a set of functions, like a certain class of functions that are the product functions. But at least we get a function on this big space, on a large set of degrees of freedom. And the product itself is relatively cheap to represent numerically, because what we have is n functions of one dimension, or three sometimes, but this is much easier to represent than a function on n degrees of an arbitrary function on n degrees of freedom. So the point is that even at a low computational effort, a Hartree product can give you some ballpark number. While if you try something like this, you set up a grid on these degrees of freedom, that cannot accurately represent a function sometimes for the same effort. Because maybe you get, like, I mean, I'm just example here, maybe you get 2 grid points in each degree of freedom for the same numerical effort or something like that, in which case, what do you mean it's not even possible to represent a function? So to understand a little bit more about what the Hartree product is and how it's limited, we can compare this to what it means to put a basis on this large space that we want to represent a function on. Well, let's assume that we can construct a set of basis functions for each degree of freedom individually. So we have phi1 of x1 and so on up to phi n of xn. So maybe I should have said here, I'm using these exponents on psi and phi to denote which degree of freedom, right? So it's not some kind of exponentiation, obviously. It's just I'm running out of places to put indices quickly. So the degree of freedom goes in the exponent. Right, and then we have, in each degree of freedom, we have some number of functions, probably infinitely many, or k of them. And if from a basis of each degree of freedom, we want to create a basis for all degrees of freedom together, we have to form products of all possible combinations of basis states. So we will have, the first one will be phi1, 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 and so on. And the next one is phi1, 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 and then phi2 at the end, and so on. And then we take all permutations, or all combinations rather, of these functions. And them taken together, of course, creates a huge set of functions. It started with infinitely many, perhaps, so it's still infinite, but it's infinite in a more annoying way when we want to represent it numerically, right? So the Hartree product basically corresponds to a single basis state, basis function on this space, right? It's also just a product of single functions of a single dimensions, which means that it's missing a lot. You know, like it's just picking one of those basis states. So it's a lot is missing if we want to be able to describe arbitrary functions. But as I said, we are able to describe a function. And we can compensate for this limitation of the Hartree product by being careful about how we select the single particle functions that go into it. So we can have some freedom there, right? So we mitigate the limitation with some freedom of choice for these functions psi in the Hartree product. So for each psi k, we construct a finite basis for that degree of freedom, and then we can a combination in this finite basis allows us to have some freedom in what kind of function for 1 degree of freedom we actually use. So examples of basis. Apologize for these. I just pulled some ugly pictures of the internet, but okay. For instance, in this situation, what kind of functions can you use here? Well, if you have bound states, maybe harmonic oscillators, eigenfunctions, a couple of those. For angular coordinates, Legendre polynomials are apparently useful. If your degree of freedom is not a single degree of freedom, but actually 3 degrees of freedom, so that the x's are actually xy, like xyz, then maybe spherical harmonics can be used as basis functions. Imaginary exponentials, that's actually the same as using a sort of a Fourier transform scheme. I don't exactly know. I'm not sure if I can answer any follow-up questions on that, but it seems natural, right? Because the Fourier transform is just expressing a function on a grid in terms of imaginary exponentials. Or maybe if you're solving a infinite square well problem, which is obviously kind of not useful for practical situations, but just as an example, then sine functions would be a natural choice here because they are the eigenfunctions of the infinite square well. But the point is that depending on the problem, you choose different bases in order to represent your Hartree product. So, yes. So right, and we want then to work towards describing the MCTDH method, but we're not going to start with that. We're going to start with TDH, so time-dependent Hartree, so without the multi-configurational. And then understanding the time-dependent Hartree method allows us to sort of at least wave our hands around a little bit and feel like we understand the multi-configurational time-dependent Hartree method. So the wave function then looks like this, and for simplicity I'm now going to restrict myself to just 2 degrees of freedom, so that the formula get rather simple. But the sort of the generalization to any number of degrees of freedom is not. It's not that complicated to understand how that's going to look. So what we want is a wave function of x1 and x2, and it should evolve in time, so t. And we make a Hartree product, psi1 and psi2, and we also have a coefficient, time-dependent coefficient a. So this is the construction that you use for this method. And then, to the best of my understanding, then this psi1 and psi2 are expressed in terms of each of them a basis. So phi1 of phi, these phi functions, right? So and the time dependence in the functions lives in the lives in the time dependence in the coefficients. But there are mentions in the material that I've read about schemes called discrete variable representations, also known as pseudo-spectral methods, that I haven't fully been able to wrap my head around completely. So I'm just saying that there probably is some freedom here in what strategy are you using to represent psi1 and psi2 that goes into the wave function. But it's clear that they are built on a basis anyway for each degree of freedom. Right? And then, okay, so a good point, one important thing to see about this wave function is that it contains too much freedom. say, for instance, I could take psi2 and normalize that to 5. Then I can still renormalize psi1 to 5 and then psi2 to 1/5. And then I would have a normalized function as long as A is just a phase, even though each of the basis function, each of the product functions are not normalized. So this freedom is kind of unwanted. So one constraint that we're going to impose on this method is that we normalize these single particle functions, psi1, psi2. And this and then of course forces A to also be normalized if we want the whole wave function to be, which we do. So A is a phase. Secondly, we're going to change, we're going to allow for these psi1 and psi2, the single particle functions, to change with time, but not in any odd way. So we're going to restrict the time evolution of these functions to be orthogonal to their current state. So psi1 in a product with a change in psi1 is just 0. They are orthogonal, meaning that if you see psi as a vector in Hilbert space, then it's rotating around, and the norm of it doesn't change. So the first constraint says that the single particle functions are initially normalized, and the second constraint keeps them normalized through time evolution. And then what we want to do now is to find equations of motion for these, for A and psi1 and psi2, because we are solving an initial value problem here, time-dependent method. So we don't care so much about eigenfunctions, but we want to express how these functions then evolve according to the Schrödinger equation. So I'm just going to keep the Hartree product that we're using here on top, so you can have a look at that while I'm talking. And then we're going to use something called the Dirac-Frenkel variational principle, which I think is a talk in itself. And I haven't been able to spend enough time to really make sense of this in my own head. But it restricts the variation or it defines the variation of the wave function anyway. So with the Dirac-Frenkel variational principle, which you can see here, together with those constraints that I showed you in the previous slide, we can derive equations of motion, even though I'm not going to bore you with each step of this derivation. You can have a look at this material here for derivations. So instead, what I want to point out is the fact that we can find equations of motions for A, psi1 and psi2. So if we take a look at the first row there, it's it's an I, and then the time derivative of A is simply the energy of the system, right? So it's the Hamiltonian in brackets, that's just the energy of the system under the wave function, and so that then defines how quickly A as a phase rotates. So the higher the energy, the quicker the phase A of t will rotate. And then psi1 and psi2, those evolve according to a little bit more complicated equations here, but you can kind of understanding them as this H1 is the Hamiltonian for the first degree of freedom when we remove the second degree of freedom from the Hamiltonian. So we multiply with psi2, and this is like an average Hamiltonian for the first degree of freedom. So it's not necessarily an exact Hamiltonian. And then since the the coefficient is taking care of the rotation due to the total energy of the system, we subtract this rotation from psi1. That shouldn't be in there, right? And because then we take that rotation twice, but we should only take once. And the same for psi2. That's sort of how that time evolves is defined by a Hamiltonian for those degrees of freedom when we take the full Hamiltonian and remove the degrees of freedom from the first degrees of freedom. So let's keep these our wave function and the equations of motion, and I'll give you two examples. So if we work with a Hamiltonian like this, where we have some kinetic energy in the first degree of freedom, we have kinetic energy for the second degree of freedom, and then a potential in each degree of freedom. These equations of motions, the time-dependent Hartree equations of motion, they work absolutely great. But if we have a Hamiltonian like this, where it's the same except the potentials are now multiplied together, then you can do a derivation to show that we're introducing errors into our problem. And I'm not going to show that to you, but it's in the material. So the difference between the first and the second is obviously that the first one can be just separated into a Hamiltonian for the first degree of freedom and a Hamiltonian for the second degree of freedom, just added together, whereas the second one cannot be separated like that. So then this is introducing errors into the time-dependent Hartree method. And it's these errors then that we're going to go after in the multi-configurational time-dependent Hartree method. Let's take an example when we now extend the time-dependent Hartree method to the multi-configurational case. And the example I want to show you is just, so we have, instead of a single function for each degree of freedom, we have now 3 single particle functions and 2 degrees of freedom. Still have 2 degrees of freedom, right? We had that in a previous example, and now also 2 degrees of freedom. But we want to add more functions for each degree of freedom. So instead of 1, we choose 3. And the wave function looks like this now. So as you can see, it's kind of get complicated quickly. We're still describing psi of x1, x2, and t. And the exponents on these psi functions in this horrible mess, they are still referencing which degree of freedom. But now the subscripts are which function for that degree of freedom. So those are then the highlighted, the pink ones are the selection of which basis functions, and we have 3 of each. So these indices goes from 1 to 3, and we have all combinations, right? Just like when we're creating a basis for a Hilbert space, we take all combinations of these functions. And then each product of this gets a coefficient. So previously we had just a single a, and now we have multiple coefficients. And you can tell that this function is not so, it gets messy enough that the previous one was easy to have a glance at to understand what's going on, but this one is not very helpful, honestly. So actually we might as well talk about it in the general case. So I'm going to follow the material here and switch to a notation where we actually just have n, or actually f dimensions, and the formula looks horrible. It's just, you don't need to understand all the details here in order to follow what I'm talking about. Just like, think about the general case is on the bottom is trying to describe what I have on top, but just for arbitrary number of functions in arbitrary number of dimensions. What it is just a sum of these products where all combinations are taken into account, and each product gets its coefficient a, and then it has a lot of indices because there's just a lot of these products. So let's keep this one in our discussion, and just like in the time-dependent Hartree method, we need to impose constraints on this wave function because right now it has too much freedom that we don't, that's not useful and will only become a problem. So the first one is just the same condition as before, that the psi functions are orthonormal. They are normalized and orthogonal. Looks a bit complicated here, but this is all that this equation says. And the second condition gets worse. So it looks like this. Instead of saying that each psi is going to evolve orthogonal to its current state. We're going to make it follow this equation, which correlates, it seems to correlate anyway, it's some J and L with the G here, like a Hermitian operated G sandwiched between the states in the on the right hand side. So this took me a while, but staring at this I could soon see that if we just, okay, we have an inner product with psi j kappa is which degree of freedom on the bra in both here, so I can basically just put that inner product to the side for a moment and then take the minus I to the other side, and then what I'm left with is this, that I have I d dt of some state equals a Hermitian operator times that state. So this is basically just a Schrödinger type equation. G is not necessarily, it's not the Hamiltonian at this stage. It's sort of going to be soon, but this is not as horrible as it seems, because it describes the type of evolution as the same as the Schrödinger equation. So, but this is then how it's expressed. Fine. The important part to note about this, since it is a sort of Schrödinger equation, this condition, though more complicated, also preserves the norms of the states. So just like we did before, we are going to apply this Dirac-Frenkel variational principle and include these constraints that I just discussed to get the MCTDH equations of motion. And brace yourselves, because they're not pretty and they're so ugly that we're not going to discuss them, because honestly all of these symbols have definitions of their own that would force me to put in more slides. So let's just skip trying to understand this and just conclude that there are equations of motion, right? So we have on the two left-hand sides here, we have the change in AJ, so the change in all of the A coefficients over time. And we have the change in the second equation, we have the change of all the psi's in time. And this is well defined in terms of then the Hamiltonian of the system and this G thing that we included in the constraint. So if we were using the same constraints as the time-dependent Hartree method, just remove every place you see G here, all those drop to 0, right? That would be the equations of motions for the time-dependent Hartree method. But we have this G here, so they look a bit more involved. And now it's time to start using the, like, you might ask why we introduced this G, and I was very I didn't understand that myself to begin with, but it has a benefit. So we're now going to use these G things to become a part of the Hamiltonian. So if H equals a Hamiltonian, so if the main Hamiltonian is on the form that it has a sum over Hamiltonians for each degree of freedom. So there is some Hamiltonian that just a part of it only relates to that degree of freedom. That's quite common. Like you have some bosonic degree of freedom, perhaps you have some other degree of freedom that has its own evolution irrespective of what it's interacting with. And then you have a rest, like HR, any kind of interaction between different systems, between different degrees of freedom, goes into this HR. Then what we do is that we have a G kappa, so there is a G matrix for each degree of freedom, and we just define that to be that Hamiltonian for that degree of freedom. This means that, let's see how to move out, the basis functions are taking care of the time evolution that is intrinsic to that degree of freedom, or the basis functions, or rather perhaps the single particle functions, the the size that we use to construct our full wave function, they will do time evolution that corresponds to that degree of freedom. And the numerical effort that we're spending to use this method, mainly goes into calculating the A coefficients, and then we don't need to include that time evolution that comes from the Hamiltonian's small h's, so to speak. That's already represented in the basis functions, and the A coefficients will only evolve according to this HR Hamiltonian, the part of the Hamiltonian that's sort of global, acting on interaction terms and things like that. This then simplifies honestly, there is a lack in my understanding exactly how this is then implemented in detail, how the size are time evolved, but I'm suspicious that you can do this almost sort of analytically, that the size, if you know a simple time evolution dictated by the small h's for that degree of freedom, then you don't really need to put that into your simulation, because you can keep track of that time evolution separately, and all you need to put into your numerics is the time evolution of the A coefficients, because those have the complicated behavior where subsystems or degrees of freedom are interacting with each other. Anyway, that's my guess, but maybe there is some keeping track of the single particle functions as well, and you can just sort of pull them apart so you can do them separately in these simulations. So that's it. There are some versions of MCTDH that I can mention. What I've discussed so far is when you want to do time evolution for nuclear coordinates, basically doing chemistry with this method. But this method is also used for things like Bose-Einstein condensates and other kinds of systems. And then there are versions, there is an MCTDH-B for treating bosons. There is an MCTDH-F for treating fermions. And there's an X when you want to have both in your system. There is perhaps some interaction between a Bose-Einstein condensate or some photons or something like that. I'm not sure, but both of these particles are included then in the X method. So, conclusions. One thing to point out here that I want to make clear to everybody is that MCTDH uses similar principles as post-Hartree calculations. They are fundamentally different because in Hartree calculations and the related species, we're trying to solve the eigenvalue problem, right? But in MCTDH, we're doing the time evolution, so we have an initial value problem. But the methods and the thinking is sort of the same. We have a function on a horribly large space, and we restrict it via this product of functions, and then we can sequentially try to add more freedom to this function by adding more products, adding more Hartree products, or in the case of quantum chemistry, we include more and more slated determinants. Another point is that when you're using MCTDH, after time evolution, typically anyway, there is still some remaining work. Or at least this is my current understanding of this. If you're doing if you're trying to do the same calculation but on a grid, which of course that's what we're doing a lot, and that's a useful method. That's rather straightforward. That's kind of intuitive what you get in the end. Like you get the wave function back, and that's on the grid as a function. It's easy to interpret. It's sort of easy to deal with in terms of I want to calculate some expectation values. It's a little bit more complicated here because you have what you get are the A coefficients, the coefficients in front of each product, and then also what functions went into the product to describe the state of the system. So you may have to go through a few steps if you, for instance, want to get the density distribution out. How is the density of the wave function distributed on my coordinates? Well, you have to do a few steps of computation. It's just not taking the wave function, squaring it, and plotting it. Or taking the square, the absolute square, as it is when you're working on a grid. So this is the third point, is sort of my own summary from reading about this, that understanding and using MCTDH does require some work because of this not so straightforward interpretation of the wave function, and just how these equations are derived, the equations of motion, and what kind of limitations they pose, how to choose the basis functions for your degrees of freedom to describe the single particle functions. I think that's probably not obvious all the time. I mean, at least that could potentially pose a problem. Error estimates, I'm not sure how they work in this case. I haven't gotten to this actually. I'm sure that this material probably includes some discussions of errors and things like that, and I haven't gotten to it. I'm just cautious that it could be a bit intricate here, because when you're working on grids, you basically are able to describe any function. That's not true. You're limited to in how quick oscillations can be, right? But that's kind of what you need to keep track of, that your kinetic energy of the system doesn't exceed the capacity of the grid. And then if it does, you have a problem. If it doesn't, you're fine. Here it's a bit more subtle, right? Because you've initially restricted yourself to what kind of functions you're able to describe. So I'm guessing that error estimates could be more difficult to deal with in this method, but I haven't read anything about it. But this is just like my own. I would be cautious about this. And that's it. So thanks.